let's talk about equilibrium. If the net force on an object is 0, you know it will stay at rest or keep moving at constant velocity. Now, we're not going to talk about the second version. We're going to do objects at rest. Essentially, we're just going to do things hanging from ropes. So I'm going to start with, I'm going to hang a 20 kilogram sign from the middle of the rope. So this rope makes an angle on each end with the horizontal at, sorry, that was supposed to be a 10 degrees. And the question is, what's the tension on each side of the rope? So we start by making a free body diagram. So we have our object. We have Ft1 and Ft2 and the force of gravity. And if you remember when I had you do free body diagrams before, I like to write numbers on these diagrams. But I have angles. Now I usually draw my angles, since this is to the horizontal, instead of doing it at the top of the rope over here, I put it at the bottom, still at the horizontal. So I've just moved it. Remember, alternate interior angles are equal, parallel lines cut by a transversal. So these are both 10 degrees. And so I'm going to redraw this diagram again. And I'm going to get rid of Ft1 and Ft2 and replace them with their components. So I have Ft1y and Ft1x and Ft2y and Ft2x. Because 2 pulls to the left and up, 1 pulls to the right and up. So I've just transferred that. Now, this sign is staying at rest. That means everything has to cancel out. So Ft1x has to be equal to Ft2x. And Ft1y plus Ft2y has to be equal to Fg. I don't know why I did that one in red. Whatever. So remember how to calculate components. We do not know these tensions. I don't know what Ft1 is and Ft2 is, but I know the x component is the cosine. So this equation turns into Ft1 cosine of 10 degrees equals Ft2 cosine for its angle, which is also 10 degrees. So this is an important equation, though it's not incredibly useful. If this is cosine of 10 and cosine of 10, that cancels out. And we have proved that the tension in the two sides of the rope is equal. It doesn't tell us what they are, but it tells us they're equal. So now we can go into this equation. I know Ft1y is the sine of the angle, plus Ft2y is again the sine of the same angle, equals Fg. Let's go ahead and calculate it. 20 times 9.8 is 196 newtons. Now here's the important next step. I couldn't solve this because I have two unknowns, except it turns out they're equal to each other. So Ft1 and Ft2 are the same. So I'm going to get rid of Ft2 by replacing it with Ft1. Ft1 sine 10 degrees plus Ft1 sine 10 degrees, because they're equal, equals 196. And then I can combine these. 2 times Ft1 sine 10 degrees equals 196. And then I divide both sides. And so Ft1 equals 196, clear, 196 divided by 2, divided by the sine of 10 degrees. I get 564 newtons. So I finished my problem. Ft1, if we pull back up here, is 564 newtons. Ft2 is also 564 newtons. So to pull this cable this tight, that it's only 10 degrees, and that's not really well to scale, that it's only 10 degrees away from the horizontal, that's a lot more force than just supporting the weight. And it's because we have the sideways pull as well as the vertical pull. Now, I knew that answer was going to be a lot bigger, so that's why I did this to scale. Notice my two vertical FTs are about equal to this, and my two X's are about equal to each other, but a lot longer. Also, because I knew this was going to be equal, that's why I made these two equal. I have a second example problem, which is a little more complicated. So let's turn the page. Again, I'm going to take the same 20 kilogram sine, 20 kg, but I'm going to have the ropes at different angles. This one makes an angle of 30 degrees to the ceiling, and this one makes an angle of 70 degrees to the ceiling. So before we start, which one is going to have greater tension? I know that because this one is closer to vertical, it's going to support more of the weight. And I did this with the students in AP1 last year. We had the ropes and we held them at different angles, and I'll pull that back out for y'all tomorrow in class. So if I draw my free body diagram, I know that FT2 is going to be a whole lot more than FT1. So I'm going to draw it same angle, but I'm going to make it pretty long, FT2. And then here I'm going to make shorter, FT1. And of course there's FG. And then I'm going to do the same thing and make my component diagram. So 20 kg, FG is already vertical. Instead of FT2, FT2y, and FT2x, and FT1y, and FT1x. Now I did go ahead in my drawing and make the two x components equal, because they have to be equal. If they're not equal, they don't cancel out. The sign's not in equilibrium, it's swinging left or right. So I know these two components are equal to each other. We have a slightly different situation, however, than the last problem. Yes, FT1x equals FT2x, but now the angles are different. Sorry, yes, that's my phone. Decline. FT1 times the cosine of 30 degrees has to equal to FT2 times the cosine of 70 degrees. So FT1 and FT2 are not equal this time. In fact, because this is the bigger angle, and with cosine as it increases, the value actually decreases. This is one of the things that tells you that FT2 has to be bigger. So we stop there, we can't do anything more. We can go to the y components. FT1y plus FT2y equals FG. So FT1 sine 30 degrees plus FT2 sine 70 degrees equals, and remember 20 kilograms, we did the weight on the other one. This is 196 newtons. So on the previous one, we could substitute in that the two things were equal, and then we finished solving. We have to do a slightly more complicated substitution. I'm again going to solve this for FT2. So that's FT1 times the cosine of 30 divided by the cosine of 70. And I'm going to put that whole thing in for FT2 right here. So FT1 sine 30 degrees plus FT1 cosine 30 degrees divided by cosine of 70 degrees. And that's just the red circle. Then times the sine of 70 degrees equals 196. This is a good time to put all these numbers in the calculator. So the sine, clear, sine of 30 degrees is 0.5. So let's make some space. 0.5 times FT1 plus, I'm going to do the cosine of 30 divided by the cosine of 70 times the sine of 70, and we get 2.379 times FT1. So, you know what, let me just double check that. Cosine of 30 times sine of 70 divided by cosine of 70, close parentheses. Yeah, I got a totally different number because I hit the wrong key. Let's try that again. Sorry for the delay. Nope, I did get the same number. Okay, So that's equal to 196. We're almost done. These two are the same variable. So if I do 2.379, I'm going to keep some more digits. It was 38 plus 0.5. I have 2.87938 times FT1 equals 196. And so FT1 is 196 divided by that number, and we get 68.1 newtons. We're not quite done because we just found FT1. We still need to find FT2, but we don't have any more algebra we have to do. FT2 equals FT1, so 68 point, I'm going to keep more digits, 0702, times the cosine of 30 divided by the cosine of 70. And I get, make sure it's on the screen, times cosine 30 divided by cosine 70. And I get 172 newtons. So, back to the original diagram. FG was 196 newtons. FT2 was 172 newtons, and FT1 is 68.1 newtons. So as expected, tension 2, because it's closer to vertical, supports more of the weight, and so it's a bigger tension than FT1. I know this was a lot of numbers. Don't get lost in the numbers. Stick with the ideas. All the components have to cancel out. The x components have to be equal, the y components have to be equal. And if they're unequal, the one closer to vertical is supports more of the weight, so the tension is greater.